Good morning students, this is Latif sir. In this video, today I will discuss about how to calculate the cell potential. Cell potential or EMF of a cell, EMF of a galvanic cell, which is represented as E cell. And in the last video, I have told that every electrode has a specific value of electrode potential. If oxidation reaction is taking place at the electrode, then the electrode potential will be oxidation electrode potential. And if reaction is taking place at the electrode, then the potential of the electrode is known as reduction electrode potential. Okay. And during calculation of cell potential, you have to use only reduction potential of both the electrode, and you can convert the oxidation potential of the electrode into reduction potential by changing the sign of the electrode potential. Okay, so what is electrode potential? What is cell potential? It is the difference between the electrode potential of the two half cell of a galvanic cell. Okay, so difference between the electrode potential of two electrode, and again I want to mention you that the electrode potential must be in terms of reduction potential. Okay, both the electrode potential you have to convert into reduction potential. Okay, and E cell is equal to E cathode minus E anode, where E cathode is the standard reduction potential of cathode, and where E cathode is the reduction potential of cathode and E anode is the reduction potential of anode. And this cell potential also known as EMF of the cell. You can also calculate EMF of the cell using this formula: E cell is equal to E right minus E left, because the cathode is always placed on the right side, and on left side you have to place the anode. Okay, in the galvanic cell. Now if we take the standard value of electrode potential, then the cell potential is known as standard cell potential, which is represented by E cell. Okay, so E0 cell, that is standard cell potential, is equal to E0 cell standard cell potential is equal to E0 cathode minus E0 anode. That is standard cell potential, standard EMF of the cell you can calculate using the standard electrode potential, standard reduction potential of both the electrode. For example, for a Daniell cell, in Daniell cell, zinc electrode and copper electrode are used, and copper electrode act as cathode, and zinc electrode is used as anode. Okay, so E0 standard electrode potential of copper electrode, Cu2 plus slash copper, you have to represent like this. This is the electrode potential of copper electrode is equal to 0.34 volt, and standard electrode potential of zinc electrode, which is represented like this, Zn2 plus slash Zn, as a reduction potential. Zn2 plus to zinc, it is a reduction. So E0 of zinc electrode, standard reduction potential of zinc electrode, the value is minus 0.76 volt. Okay, so the standard cell potential of the Daniell cell is equal to E0 cell is equal to E0 copper 2 plus slash copper minus E0 Zn2 plus slash Zn, where copper 2 plus slash copper, this is cathode, and Zn2 plus slash Zn is the anode. Okay, so E cell is equal to 0.34 minus 0.74, that is 1.10 volt. Okay, so standard reduction potential of the Daniell cell is 0.10 volt. Now see what is reference electron. It is not easy. It is not easy to measure the electrode potential of different electrode, different half cell directly. But you can calculate, you can measure the electrode potential of different electrode with respect to some other electrode. Okay, and these are known as reference electrode. So what is the reference electrode? The electrode of known potential. The electrode of known potential is called reference electrode, and it may be primary reference electrode like hydrogen electrode or secondary electrode like calomel electrode. Standard hydrogen electrode, which is represented as SHE, the short form is SHE, standard hydrogen electrode, is also known as normal hydrogen electrode, that is NHE. It consists of a platinum wire. This is the platinum wire. It consists of platinum wire. You can see in the figure 3.3. Standard hydrogen electrode, which is a reference electrode, it consists of platinum wire carrying platinum foil coated with finely divided platinum black. Here platinum wire, platinum foil which is coated with finely divided platinum black, and the wire is sealed into a glass tube, and the wire then placed in beaker containing 1 molar HCl solution, and in this beaker 1 molar HCl solution you have to take. Okay, and then you have to dip this platinum wire into the solution, into the 1 molar HCl solution, and then hydrogen gas at 1 atm pressure is bubbled through the solution at 298, that is 25 degrees Celsius. Then you have to pass hydrogen gas through the solution at 1 bar or at 1 atm pressure, and this total arrangement, this entire arrangement is known as saturated hydrogen electrode. This is reference electrode, saturated hydrogen electrode, and the representation of the hydrogen electrode, the half cell electrode, is platinum comma hydrogen gas at 1 atm. You have to write hydrogen gas within bracket 1 atm slash H plus, that is HCl solution, H plus in aqueous solution, and concentration you have to tell. Concentration is 1 molar. So saturated hydrogen electrode, standard hydrogen electrode, can be represented as platinum within brackets S means solid platinum, comma hydrogen gas at 1 atm slash H plus in aqueous solution, 1 molar aqueous solution. This is the saturated hydrogen electrode. Okay, symbolic representation of hydrogen electrode, standard hydrogen electrode. And the electrode potential of standard hydrogen electrode has been fixed as 0. So E0, standard hydrogen electrode potential, H plus 2 half H2, the standard E0 of hydrogen, standard hydrogen electrode is 0, and you can calculate the electrode potential of different electrode with respect to hydrogen electrode. Okay, now see main drawbacks of standard hydrogen electrode. It is difficult to maintain 1 atm pressure of hydrogen gas in a standard hydrogen electrode. It is difficult to maintain the concentration of H plus as 1 molar. Okay, and the platinum electrode is easily poisoned by traces of impurities, and hence now calomel electrode are conveniently used as reference electrode, and it consists of mercury in contact with mercurous chloride Hg2Cl2 placed in a solution of KCl. Okay, it calomel electrode, it consists of mercury in contact with mercurous chloride, that is Hg slash Hg2Cl2 slash KCl. Okay, so this is the calomel electrode. You can use any one electrode, reference electrode, hydrogen, standard hydrogen electrode or calomel electrode. So with using standard hydrogen electrode, or using any reference electrode, you can calculate the reduction standard electrode potential of the electrode of the half cell. Now now see the cell diagram or representation of a cell. How to represent a cell? You know, a cell is made up of two electrode. One is cathode, another is anode, and these are known as two half cell. One is oxidation half cell, which is the anode, and another is reduction half cell, that is cathode. And according to convention, IPSC convention, you have to write cathode first. You have to write first you have to write anode, then you have to write cathode. On the left side you have to write anode, and on the right side you have to write the cathode. According to IPSC convention, during representation of a cell, you have to write the symbol of anode first, then you have to write the symbol of cathode, and you have to give a salt bridge in between two half cell. This is the double line is vertical to double line is known as salt bridge. So according to IPSC convention, anode half cell is written on the left hand side, while cathode half cell on the right hand side. A single vertical line separates the metal from aqueous solution of its ion. For example, copper from copper 2 plus ion. So you have to write copper 2 plus slash copper, or zinc from Zn2 plus ion. You have to write Zn slash Zn2 plus. Okay, because zinc electrode is zinc electrode is anode, so oxidation reaction take place at anode, so you have to write the anode as Zn slash Zn2 plus, and copper electrode act as cathode, so you have to write the cathode like Cu2 plus slash Cu, because reduction reaction take place. Now see cathode reaction of the Daniell cell. Cathode reaction, that is reduction reaction. At cathode, copper 2 plus accept 2 electron and it converted into copper metal. And at anode or oxidation reaction, zinc electrode loses 2 electron and it is converted into Zn2 plus ion. So the cathode is copper 2 plus 2 copper. So the cathode is, representation of cathode is copper 2 plus 2 copper. Okay, and the representation of anode is Zn2 Zn2 plus. Zinc loses 2 electron and it is converted into Zn2 plus, so the anode is zinc slash Zn2 plus. Okay, this is anodic chamber and this is cathodic chamber. Anode half cell and this is cathode half cell. Okay, so and you have to give a vertical double line to represent the salt bridge in between two half cells. So first you have to write the anode, then you have to give a salt bridge, and then you have to write the symbol of cathode. Okay, and the molar concentration of the constituent ion present in the solution, you have to write in within bracket. You have to write the concentration of the metal ion of within bracket. Okay, for example, Zn2 plus 1 molar Zn2 plus, you have to write Zn2 plus within bracket 1 molar. Okay, and the value of EMF of the cell is written on the extreme right of the cell. This is the entire cell, Daniell cell, and then the EMF of the cell is written here. EMF of this Daniell cell is 1.1 volt. So how to represent the cell, galvanic cell? First you have to write the symbol of anode, then you have to give a salt bridge, then you have to write the symbol of cathode. Okay, so anode first, then cathode. But during representation of the cell, you have to give cathode on the right side and anode on the left side. Okay, and this two half cell, cathode and anode, is connected by a salt bridge which contain agar-agar gel, potassium nitrate. So what is salt bridge? Important point, important topic. What is salt bridge? A salt bridge is used to maintain the charge balance and to complete the circuit and to complete the circuit by facilitating by facilitating uh, by facilitating the flow of ions through it. So Solbridge complete the circuit, and Solbridge making the charge electrically neutral charge in both this solution, and it contains a gel, agar-agar gel, which an inert electrolyte like the Solbridge contain agar-agar gel in which inert electrolyte like sodium sulfate, potassium nitrate are mixed. A negative ion of this electrolyte flow to the anode and positive ion flow to the cathode through the Solbridge, and the charge balance is maintained and cell keeps on functioning. This is the role of Solbridge in Daniell cell. Okay, it makes the Solbridge makes the charge on the both half cell neutral. Now see Nernst equation. What is Nernst equation? Nernst equation, using this equation you can calculate the electrode potential or cell potential of a, okay. So Nernst equation, very important equation. Using this equation you can calculate electrode potential or cell potential. Okay, so for a general electrochemical reaction, if this is the reaction Mn plus Ne implies M, this is a reduction reaction. The Mn plus ion accept n number of electron and it is converted, it become neutral atom, M atom. So for this reaction, for this cell reaction, the EMF of the cell can be represented. This is actually a electrode reaction. Okay, for this electrode reaction, this is cathode actually, because reduction reaction is taking place. So so electrode potential of this electrode Emn plus slash M is equal to E0 standard electrode potential of this electrode, E0 Mn plus slash M minus 2.303 RT by NF into log concentration of the product, that is M is a solid product, so its concentration you have to take 1 divided by concentration of Mn plus ion. Okay, so this is the formula, Nernst equation for the calculation of electrode potential. Similarly, for a cell reaction, if the cell reaction is small a capital A plus small b capital B implies small c capital C plus small d capital D, the E cell EMF of the cell, that is E cell, will be equal to E0 cell or E naught cell, that is standard cell potential, minus 2.303 RT by NF, where N is the number of electron involved in the cell reaction, into log concentration of product divided by concentration of reactants. So E cell is equal to E0 cell minus 2.303 RT by NF log C to the power C, D to the power D, A to the power A, B to the power B. This is the Nernst equation for a cell reaction. Okay, so using this reaction you can calculate the EMF of the cell. Okay, and here it is mentioned that for concentration of pure solid and liquid you have to take 1 unity. Now see, at equilibrium E cell is equal to 0, not E0 cell, E cell potential is equal to 0, but not the standard cell potential is equal to 0 at equilibrium. So at equilibrium you can write E cell is equal to 0, so E0 cell is equal to 2.303 RT by NF log concentration of product by concentration of reactant, and this is actually equilibrium constant. This is the equilibrium constant Kc. Okay, so at equilibrium this ratio of concentration of product by concentration of reactant is known as equilibrium constant. Okay, so at equilibrium you can write E0 cell standard cell potential at equilibrium is equal to 2.303 RT by NF into log Kc, and at 25 degrees Celsius or 298 Kelvin temperature, the value of 2.303 RT by F, the value of 2.303 RT by F is equal to 0.0591. So the standard cell potential is equal to E0 cell is equal to 0.0591 divided by N into log Kc, where Kc is the equilibrium constant. Okay, so this is the relation between equilibrium constant and standard reduction potential of the cell. One example is given here. Represent the cell in which the following reaction takes place. The reaction is given: Mg magnesium solid and 2Ag plus, and concentration of Ag plus is given 0.0001 molar, implies Mg2 plus and concentration of Mg2 plus is 0.130 molar and plus 2Ag solid, and you have to calculate the cell potential E cell. Here E0 cell is given, E0 cell is 3.17 volt. So cell reaction is given. So the cell is the oxidation half is Mg2 plus. This is anode, and Ag plus to Ag is the reduction. Okay, so the oxidation anode is Mg2 plus, and then you have to give salt bridge, and then Ag plus to Ag is cathode. Ag2 plus to Ag is cathode, and concentration you have to write within bracket. So the cell potential E cell is equal to E0 cell minus 2.303 RT by NF, by here the number of electrons involved N is equal to 2 into log concentration of Mg2 plus divided by concentration of Ag plus whole square. This is the formula. So you have to put E0 cell is given, and at 25 degrees Celsius value of 2.303 RT by NF, 2.303 RT by F, the value of this constant is 0.0591 divided by N. N means N is equal to 2. So E cell is equal to 3.17 minus 0.059 by 2 into log 0.130 divided by 0.10001 whole square. So the value will be equal to, E cell will be equal to 2.96 volt. Okay, and the last part, what is the relation between Gibbs free energy change and E cell of the reaction, cell potential of a reaction. Okay, so delta G is equal to minus NF E cell. Gibbs free energy change is equal to minus NF. F is the Faraday constant, and the value of F is 96500 coulomb. 1 Faraday is equal to 96500 coulomb, and N is the number of electron involved in the cell reaction. So the relation between Gibbs free energy change and E cell is equal to delta G is equal to minus NF E cell. Okay, and if the Gibbs free energy change is negative, then the cell reaction will be spontaneous, and if Gibbs free energy change is positive, then the cell reaction will be non-spontaneous. And if you take the standard cell potential, then you will get the standard Gibbs free energy change of the cell, that is delta G0 is equal to minus NF E0 cell. Okay, so thank you students, and one thing, you have to solve many numerical problem based on this Nernst equation. You have to calculate cell potential, you have to calculate the concentration of ions present in the solution. Okay, thank you students.